We were talking about vectors for some time, and now let me show you one generalization of what we understand for vectors at this moment. We were thinking about vectors as intervals of real numbers. That can be visualized as an arrow in a plane or in a 3 or more dimensional space. But this can be generalized to a much more general, to much broader sense. So the term linear vector space, sometimes called only vector space or sometimes only linear space, is the following. Consider a set that is not empty. If the elements in this set can be added, that means we have some operation addition. And if these elements can be multiplied by a real number, by a real scalar, let us denote these operations plus, the addition, and dot, not for the dot product, not for the scalar product, but this is the multiplication of a number with a vector. The elements of this set will be called vectors. Then we say this triple is the linear vector space, or this set equipped with these two operations is the linear vector space, if the following 8 conditions are satisfied. They are very general, very natural, very obvious. So quite many sets do satisfy these conditions. We want a plus b be equal to b plus a for any 2 vectors in the set V. This is called commutativity. Well, some operations satisfy this, right? We want a plus b plus c be equal to a plus b plus c if we add in this order. This is called associativity. Then we want that there exists an element 0 such that when added to any vector A, the result is the vector A itself. And we want for all vectors A in the set V to exist some element minus A such that when we add these two we get the 0. This is the additive inverse. And we want, if we take the number 1 times any vector A in the set V, we get the same vector A arrow. And now we want this to be true for any vector A arrow and any 2 scalars, alpha and beta. Namely, if we add the scalars and multiply by the vector, we want to get the same result as if we multiply the scalar with the vector with these 2 scalars and we add these 2 vectors. In this line, observe that this plus and this plus have different meaning even if we use the same graphical symbol, which we shouldn't actually. This is well, I don't like it. This is addition of real numbers, but this is addition of vectors. This is called distributive law. And this is another version of the distributive law. This time we want this to be true for any 2 vectors, A arrow and B arrow, and any scalar alpha. Namely, if we add the vectors and then we multiply by the scalar, we want to get the same result as if we multiply the 2 vectors with the scalar and add the vectors. And once again, this is the addition of vectors. This is also addition of vectors. Right. Well, yeah. Well, and the final condition is that for any 2 scalars, alpha and beta, and any vector A arrow, this should be true. If we multiply the scalars and then we multiply by the vector, we want to get the same result as if we multiply the scalar, the vector with the 1 scalar and then with the other. And now again this time, observe that these 2 dots, even this is the same graphical symbol, represents a different mathematical operation. This is multiplication between scalars, between numbers. And this is a multiplication between a scalar and a vector. Many sets with natural operations, addition and multiplication, do satisfy these conditions, also called axioms. So let me give you a few examples what is and then what is not a linear vector space. Rn is a nice example of a linear vector space. Actually, this comes as a generalization. If we play with the vectors in Rn, we observe that this is true. And then we say, and what about other objects, other sets? Could this be true even for them? And it turns out, yes, it can. By Rn, we mean R, namely the line. We mean R2, namely the plane. We mean R3, namely the three-dimensional space, the space we believe we live in. N can be even 0. This is a very, very small set. Just a set containing one single element, namely 0. One single point. This is trivially true because on the left and on the right of each of these is 0 equal to 0. So one point, or a line, or a plane, or a space, or a set of n tuples of real numbers are perfect examples of a linear vector space. We can consider not only finite n tuples, we can consider also infinite sequences, because we can add infinite sequences and we can multiply them by a scalar. Another example of a set that can be considered a linear vector space is a set of ordered matrices with fixed dimensions, n times n. And what is very important, the set of functions. And we can put some conditions for functions that we want to consider. Say, functions defined in some interval, say 0, 1. Or functions that are continuous in such an interval. Or functions that are continuous and have continuous derivative in the chosen interval. Or functions that are continuous and have 2 or more, or any number of derivatives. Or some subsets of functions, say polynomials of order not more than 5. Yes, this is a nice example of a vector space. Functions are considered as vectors in quantum chemistry and quantum physics. Well, and some examples of a set that is not a linear vector space. If you take anything of that and you take just a boundary subset, say, if you start with R2, that means the entire plane, and if you take only a square, say unit square, just this square, equipped with the same addition and multiplication as for Rn. This is not a linear vector space, because if you take these two vectors, then you fall out. And we want the addition to be defined for all A and B in the set. Defined means the result is again in the set. Also, the multiplication by a scalar means that for any A and any alpha, if alpha is a real scalar, if A is a vector, then we want A alpha to be defined as a vector. That means it must be also in the set V. That means if the set contains some vector, some non-zero vector, then any multiple, even a large multiple, if you multiply by 1000, then you get a very long vector, but you still be in the set. So if it goes some way, it can't stop. It must go in the direction to infinity. So if it is bounded, no chance to be a vector space. Well, now when we have the term linear vector space, we can define another very important term linear map. Not to be confused, the word linear here is the adjective to the space. And here this is the adjective to the map, a generalization of a function. So linear vector space and linear map are two different things, two different objects. So consider two linear vector spaces, U and V, and consider a map, let's call it capital L, from U to V. And we say this map is linear if these two conditions hold. L, A plus B is LA plus LB. In other terms, image of sum is equal to sum of the images. And the second condition is that L alpha A is alpha LA. And this should be true for any AB from the set U, and this should be true for any A from U, and any alpha from R. Well, actually, we can write these two short conditions as one longer, namely L alpha A plus beta B is equal to alpha LA plus beta LB, which can be written as map of a linear combination is equal to the linear combination of the images with the same coefficients. And once again, let's have a look at a few examples of maps that are linear and that are not. So, multiplication by a scalar is a linear map. Multiplication by a matrix is again a linear map. Very important example of a linear map in infinite dimensional spaces is derivative. And this is a map from, not from numbers to numbers, not from n-tuples to n-tuples, but a map from a set of functions into a set of functions. We haven't worked with this kind of map yet. Function is the argument, and another function is the result. Well, and you know that if you differentiate two functions, the result is the sum of the derivatives. And if you take a constant time a function, then the derivative is constant times the derivative of the function. So the derivative as a map, as an operator, is an example of a linear map, a linear operator. And many others. And what is not linear, if there is a different operation than multiplication, say x squared, sine, logarithm, exponential, tangent, arctangent, division, all these operations give rise to a function or map that is not linear. Well, in mathematics, we say a map is linear if this is true for all vectors A and all vectors B and all scalars alpha. Yes, this is the mathematical definition. But in practice, in engineering practice, many systems behave approximately a very good linearly for weak input. And for strong input, they behave non-linearly. As an example, consider a concert or pop music singer, microphone, amplifier, loudspeaker, and nice music. The amplifier has such a characteristic. This is the input voltage, and this is the output voltage. If the singer is silent, you hear nothing. 0 maps to 0. And for small input to the amplifier, the signal from the microphone, say 100 times greater output. but the voltage, the output voltage, cannot go beyond any bound. It is saturated at least by the voltage of the battery, of the power supply. So, for large input values, it doesn't grow linearly. It is saturated like that. So you see, this is a typical behavior of real physical systems. For small input, it can be considered as linear, at least approximately. But for large input, the output grows no more proportionally to the input, and there is some saturation. As in a very extreme case, if you put 1000 volts inside, then you burn the amplifier. The result is the response is no more linear, right? So this was the practical consideration, but in mathematics we want this to be true for all A and B and alpha.